First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Here's the season to be serving.
When I was solving equations, I was feeling amazing.
All right, greetings, good people. We're talking the DISC method. This is part 3. So today we're going to be looking at the DISC method where the function is revolved about the y-axis. Prior to that, though, let's take a trip back and kind of look at what we covered before and try to watch this progression to where we are now. So when we first started doing the DISC method, as you can see on the board, the function was revolved about the x-axis, and the method we found to find the volume, which is pi times the integral from a to b of f of x squared dx. And so then we started rotating the function about other horizontal lines in addition to the x-axis, and some line of the form of the equation y equals k, and then we got the following formula, where it's pi times the integral from a to b of f of x minus k squared dx. And we, in our part 2 video, explained how that particular progression happened. So now what happens now when we revolve it about the y-axis? So I want to take a brief visual of how it looks. So I'm going to look at the function the square root of x. And this is the function the square root of x, and here's the function in blue. And here we're rotating it or revolving it about the x-axis, and it creates this particular structure. So I want you to think about, before I show, what would happen if this same function was revolved about the y-axis. Would the solid look different? Would the volume be the same? Would the volume be different? So here's how it looks being rotated about the y-axis. So here again is the function f of x equals the square root of x. Not necessarily in the same scale as in the previous picture, but this is indeed the same function. And you can see now it's being rotated about the y-axis. Now, the main thing we have to look at in terms of developing a formula is what is our radius, because that's the main part of the formula, because pi is just a constant and the height is just dx. So the real meat of the matter is the function. So if we go back and look at it when it's revolved about the x-axis or any other horizontal line, again, this was the radius, this distance from the axis of rotation to the end, and it basically was the value of the function evaluated at x. So it was a y value, but it was y equals f of x. So it was the value of the function evaluated at x. That's how we got the radius at each particular point. Well, when we're rotating about the y-axis, so this is no longer the radius, obviously, going up and down. It is no longer a y value. This is the radius. So you can see here, the radius is actually an x value, and it's the value of the function evaluated at y. So again, going back, when it was rotated about the x-axis or any horizontal axis, the radius was a function of x. It was evaluated at values of x, and it was a y value, so it was a form y equals f of x. Well, now when we rotate it about the y-axis, the radius is actually an x value, and it's evaluated at different y values, so the function is of the form x equals f of y. And so also, to go all the way back, so if you notice, when we're going about a horizontal axis, the function is y equals f of x. The limits of integration are x equals and x equals, but the function of the axis of rotation is y equals, even if it's the x-axis, because the formula for the x-axis is y equals 0. Well, if you look at it from this standpoint of rotating about the y-axis, notice the limits of integration. They're not going to be x values anymore. They're going to be y values. So when it goes about the x-axis or horizontal axis, the limits are x equals equation. When it goes about the y-axis or any other vertical axis, the limits are going to be y equals, obviously. When it rotates about the x-axis or any horizontal axis, the function which represents the radius is the function y equals f of x. Well, when it rotates about the y-axis or any other vertical axis, the function for the radius is x equals f of y. And so therefore today, our formula for finding the volume is the following. So let me just read what this says. So to find the volume of a solid of revolution with a function of x equals f of y, rotated about the y-axis from y equals a to y equals b, use this formula. And it's pi times the integral from a to b of f of y squared dy. So the main difference as we go about the y-axis and any other vertical axis, which we'll look at in part 4, is the function is a function of y, x equals f of y, and the limits are y equals equations. Now, of course, the axis of rotation are going to be x equals equations because the equation of the y-axis is x equals 0. So being that many functions are not written in a form x equals f and y, when we do the problems, we're going to have to, in many cases, rewrite the function in x equals form instead of y equals form. So let's go ahead and look at some examples. All right, so here's the first example I would like to look at. And so just to read the question, it says, find the volume of a solid generated by revolving the region bounded by y equals the square root of x, y equals 0, y equals 4, and x equals 0 about the y-axis. Now, so this is going about the y-axis, okay? So that tells me my radius function should be x equals f of y. And it tells me my limits of integration should be y equals equation. So y equals equations. So my a obviously is 0, and my b obviously is 4. This other curve, x equals 0, is just the same as the y-axis. So really, it's inconsequential as far as the calculations are concerned. This is just the axis of rotation, which is the y-axis. So let's look at how we'll work this out. All right, so here's the situation of the problem. So again, I like to identify the main curve, the limits, if they're given, and the axis of rotation. So here the main curve is y equals the square root of x. The limits are y equals 0, y equals 4, and the axis of rotation is the y-axis. So because the axis of rotation is the y-axis, that means my main curve has to be of the form x equals f of y. So it has to be expressed as the function of y in the form of x equals. So I'm going to take this guy and basically just solve it for x, and that'll give me my x equals f of y equation. So if I take the square root of x, set it equal to y, right? So I'm just taking this curve and I'm just putting the square root of x on the left because I want to solve for x. And now I'm just want to put it in x equals form. So in this situation, all I have to do is square both sides. So I square both sides, and you'll see that x is y squared. So there it is. So there's my function. So there's my x equals f of y function. So my f of y function is y squared. So remember, to find the volume of a solid revolution being rotated about the y-axis, this is our formula. So the volume is pi times the integral from a to b of f of y squared dy. So that's our formula there. So we're just going to plug in the value. So a and b are going to be 0 and 4, and f of y is going to be y squared. So it should look like this. So y is, the volume is pi times the integral from 0 to 4 of y squared dy. So there's the guy. Always remember to have the pi there, and always remember to square the function. And I like to square it before I integrate. So y squared would be y to the 4th. So the volume is pi times the integral from 0 to 4 of y to the 4th dy. All right, so now we can go ahead and solve the problem. So the integral of y to the 4th dy, of course, will be y to the 5th over 5. So this is pi times y to the 5th over 5 to be evaluated from 0 to 4. So I don't have to worry about plugging in 0 in this case because 0 to the 5th over 5 is simply 0. And so we just plug in 4. And 4 to the 5th power is 1,024. So this is going to be 1,024 pi over 5. All right, that's how that example looks. We'll look at 2 more examples and we'll close this particular lesson now. So let's look at example 2. All right, so in the second example, it says find the volume of the solid generated by revolving the region bounded by y equals x squared, y equals 1, y equals 3, and x equals 0 about the y-axis. So again, we're going about the y-axis. So our radius function should be in the form of x equals f of y. Our limits of integration should be y equals, guys. And of course, here you see y equals 1 and y equals 3. So a is 1 and b is 3. Again, x equals 0 is simply the y-axis. So that's inconsequential as far as the calculations are concerned. So let's go ahead and work this problem out. All right, so here's the situation, my guy. So the main curve, again, is y equals x squared. There are limits. The axis of rotation is the y-axis. And because of that, we need our main curve to be of the form x equals f of y. X equals f of y, excuse me. So basically, we need to take this function y equals x squared and put it in x equals form. So let's go ahead and do that. So we'll have x squared equals y. And again, all I want to do is solve for y, solve for x. So we'll take the square root of both sides. So where x would be the square root of y, and that's our f of y. So f of y equals the square root of y. And so once we got that, so you know the formula. So the volume is going to be pi times the integral from a to b of f of y squared dy, and our a to b is 1 and 3, and here's our f of y. So the volume is going to be pi times the integral from 1 to 3 of the square root of y squared dy. So don't forget the pi, and don't forget to square the function. Of course, the square root of y squared is just y, so this is pi times the integral from 1 to 3 of y dy. All right, so the integral of y is y squared over 2. So this is y squared over 2. Don't forget the pi. Let's put pi there to be integrated from 1 to 3. So let's plug in our values and see what we get. So if we plug in 3, that'll be 9 over 2. So pi times 9 over 2 minus, we plug in 1, that would be 1 over 2. And so 9 over 2 minus 1 over 2 is 8 over 2, or 4. So our answer will be 4 pi. All right, so I hope you're finding this as easy as I am. And let's do one last example. So here's my final example. And so it says the paraboloid pictured below can be formed by rotating the graph of y equals 3x squared about the y-axis. Find a formula for the volume of the paraboloid with a height of h. So I just know that the height of this particular solid is h. All right, so this is the situation we have with this problem. So I just made a sketch of the situation. And all we know the main curve. We also know the axis of rotation is the y-axis, and we know the height of this guy is h. So of course, for the main curve, since it's going about the y-axis, I have to put it in x equals f of y form. So let's do that real quick. So we'll have 3x squared equals y divided by 3x squared is y over 3. Take the square root. So x is the square root of y over 3. So my f of y is the square root of y over 3. All right, so we have our f of y, and we have our axis of rotation, which is the y-axis, but we don't have our limits of integration. So this height is h, and where this starts and where this ends doesn't matter. I know it's h. So probably the easiest thing to do is say this starts at 0. This is 0 right here, and this is h up here. So my a would be 0, and my B would be H. Now, of course, you don't have to start at 0. You can start at 7, and your A would be 7, and your B would be H plus 7. Or you can start at 10 million, your A would be 10 million, and your H would be H plus 10 million. But it's probably easiest just to start at 0 and make this H. So we're going to integrate from 0 to H of the given function squared. So let's see how that looks. So then our volume is pi times the integral from 0 to H of the square root of y over 3 squared dy. So there's our situation. Again, don't forget the square, don't forget the pi. So let's square before we integrate. So therefore the volume is pi times the integral from 0 to H of y over 3 dy. All right, now sometimes students get confused when integrating a function like this, where it's really just a function over a constant, which really means 1/3 is just like a coefficient. In fact, I can factor the 1/3 out of the integral if I wanted to. I'm not going to, but you should have the understanding that that's just a coefficient of y. The integral of y, of course, is y squared over 2. And again, it's being multiplied by 1/3. So when I integrate y over 3, I should get y squared over 6. And if that doesn't make sense, then it's probably a good idea for you to factor out the 1/3 and then to integrate. But hopefully you can understand. If the integral of y is y squared over 2, and that's over 3, you're going to get y squared over 6. So we get y squared over 6. There's a pi there to be evaluated from 0 to H. Again, plugging in H here would give me 0. So, plugging in 0 here would give me 0. So I don't have to worry about plugging in 0. All I have to do is plug in H. And if I plug in H for y, of course, I get H squared over 6. So this is pi times H squared over 6. That is the formula. All right, so we hope what we covered made sense and gave you a good understanding of finding the volume with the disk method of solids of revolution, where the function is revolved about the y-axis. We will see you next time.
Specialized in science and math, original black men, busting thoughts that pierce your mental, the fierce, ripping your section. Vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.